So today we'll be doing Lecture 7 practice problems. So let's go to number 1. Number 1 asks, mass number versus atomic mass. To identify which element an atom is, we look at how many protons it has, right? Because when looking at an element, the atomic number describes the protons. So for number 1, to identify which element an atom is, we look at how many protons it has. Atoms of the same element but differ in number of neutrons are called isotopes. Because isotopes has different neutron count. Because they differ in number of neutrons, they will have different masses, or mass number. An atom of 1 hydrogen weighs how many AMUs? Looking at the periodic table, 1 hydrogen weighs 1.00794, which could be rounded to 1 AMU. An atom of 2 hydrogen weighs 2 AMUs, because that means there's 2 atoms of hydrogen, which has 2 AMUs. An atom of 3 hydrogens weighs 3 AMUs, because there will be 3 atoms. In nature, 99% of hydrogen atoms are 1 hydrogen. What do you think the weighted average mass of hydrogen atoms be? Look up the atomic mass of H. Does that match? Looking at the periodic table, we can figure out how much the average mass of hydrogen atoms is. So, looking at the periodic table, it says that it's 1.00794, which could be rounded to 1.01. So, when asking, what do you think the weighted average mass of hydrogen atoms be? The answer is the weighted average mass of hydrogen atoms should be close to 1 AMU. And this is true because we can see that on the periodic table, hydrogen is approximately 1.01, making it true that it could be 1 AMU. So let's go on to problem number 2, electron dorming. So we just learned that electrons of an atom live in different energy levels, radiating away from the nucleus, starting with level 1, then 2, then 3, and then 4. These energy levels are quantized, meaning discrete levels, so no electrons can be at level 1.5. For example, in this course, we will only learn up to level 4. Level 1 can house 2 electrons. So to level 1 can house 2 electrons, while the others level can house up to 8 electrons. So, for example, neutral sodium has a total of 11 electrons. If you put them in their energy levels, you first put 2 in level 1, then 8 in level 2, then the last one in level 3. Thus the electron arrangement for sodium is 2, 8, 1. Write the electron level arrangement for each of the following atoms. So let's do A. A is lithium. So the first thing we have to do is identify where lithium is at. So lithium's right here. And in the first energy level, there are 2. 1, 2. And in the second energy level, there is 1 valence electron. So that's the answer for lithium. Now let's do B, beryllium. Again, we have to locate where beryllium is. So 1, 2 in the first level, and 1, 2, 2 in the second level. C, carbon. So we have to look for carbon, and carbon is atomic number 6. So in the first energy level, it has 2, 1, 2. In the second energy level, it has 1, 2, 3, 4. Now let's do D, sulfur. In the first energy level, it has 2, 1, 2. Second energy level has 8, 1, 2, 3, 4, 5, 6, 7, 8. And in the last energy level, it has 1, 2, 3, 4, 5, 6 valence electrons. Now let's do E, helium. Helium is right here. So the first energy level, it has 2, 1, 2. Now let's do the last one, F, fluorine. So fluorine's right here. First energy level has 2, 1, 2. And the second energy level has 1, 2, 3, 4, 5, 6, 7. So now let's move on to problem number 3. It's what's on the outside that counts. Electrons that reside on the outermost energy level of the atom are called valence electrons. The number of valence electrons of an atom dictates what family it belongs to and plays an important role in its chemical reactivity. Identify the elements that have the following electron level arrangements. Then indicate how many valence electrons in each element along with the group number. So first, let's write the energy level and the group number on the periodic table. So we know that this is the first energy level with 2 valence electrons. So this is the first energy level, second energy level, third energy level. Okay, and this is the first valence electron with the group number of 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So letter A. So we know that these are the energy levels. So for A, in the first energy level, they have 2 valence electrons. So for the first energy level, we know that this element has 2 valence electrons in the first level, so it's going to be 1, 2, okay? And the second energy level has 3 valence electrons, so 1, 2, 3. So the answer is boron. And the number of valence electrons is going to be 3 from the group number. So I'll highlight it. So these are the group numbers. And the number that is above the letter is always going to be the valence electron for that column. Okay, so boron has 3 valence electrons. And the group number will be 3A. 3A. Okay, so let's do B. On the first energy level, it has 2 valence electrons. So 1, 2. And the second energy level has 8. 1, 2, 3, 4, 5, 6, 7, 8. And the third energy level has 1. So the answer is going to be sodium for the element. And the number of valence electrons is always the number for the group number. So it's going to be 1 valence electron with a group number of 1A. Let's do C. So for C, the first energy level has 1, 2 valence electrons. Second energy level has 2 valence electrons. So the second energy level has 2. 1, 2. So the element will be beryllium. With the valence electrons of 2. And the group number of 2A. So you can notice that the valence electrons is always the same number as the group number, but without the A, without the letter. Okay, D. First energy level has 2, 1, 2. Second energy level has 8, 1, 2, 3, 4, 5, 6, 7, 8. Third energy level has 8, 1, 2, 3, 4, 5, 6, 7, 8. So the answer is argon. With the valence electron of 8. And the group number of 8A. Okay, now let's do E. For the first energy level of E, it has 2 valence electron. First energy level has 2, 1, 2. Second energy level of E has 8, 1, 2, 3, 4, 5, 6, 7, 8. Third energy level has 7, 1, 2, 3, 4, 5, 6, 7. So the element is chlorine with the valence electron of 7 and a group number of 7A. So you can notice that the valence electron is always the last valence electron on the energy level. So for A, the last energy level has 3, so this has 3. For B, the last energy level has 1, so valence electron is 1. For C, the last energy level has 2, so valence electron is 2. For D, the last energy level has 8, so it has 8 valence electrons. And then for E, the last energy level has 7, with 7 valence electrons. Number 4. Again, valence electrons are super important. Let's make sure we know how to count them. So A A asks us, how many valence electrons does an element in group 5A have? So A is referring to this column, and this column has 5 valence electrons because the number that is in front of the letter is always the number of valence electrons for that entire column. So for A, when it asks us how many valence electrons does an element in group 5A have, they have 5 valence electrons. Because it's always this number right here. B, how many valence electrons does an element in group 6A have? So group 6A has 6 valence electrons. So oxygen, sulfur, selenium, tellurium, and polonium all have 6 valence electrons. C, how many valence electrons does C have? So first we have to identify where C is. So C is right here. Atomic number is 6. And it's in group 4A, meaning it has 4 valence electrons. D, how many valence electrons does sodium have? So again, we have to locate where sodium is, and sodium is right here, atomic number of 11, and we look up to the group number, which is 1A. So sodium has 1 valence electron. Last one. E, how many valence electrons does F have? So we have to locate where F is. Right here, atomic number of 9, and we look up to the group number, which is 7A, meaning it has 7 valence electrons. 5. Line them up. Part 1. How far away the electrons are to the nucleus dictates the size of the atom. Arrange each set of elements in order of increasing size based on periodic trends. Use less than sign. Summarize what the trend is going across the periodic table and going down the periodic table. So, letter A. A asks us to arrange the elements in order of increasing size based on periodic trends for Si, S, and P. So first we have to identify where Si, S, and P are. So Si is right here, S is here, and P is right here. So easier way to memorize the trends for atomic size is if it's going down, it's increasing. And if it's going to the left, it's increasing. So we have to identify the atomic size for these three. So because Si is the biggest, has the biggest atomic size, Si will be to the right. Because it has the biggest atomic size. Then it would be phosphorus and then sulfur. Because silicon has the biggest atomic size, then comes phosphorus, and the smallest one is sulfur. Let's do B now. Sn, Si, and C. So first we have to identify where Sn, Si, and C are. So where's Sn? Where's Si? Okay, Si is right here. C is right there. And now we have to find where SN are. Over here, 10. So SN, SI, and C. So remember, whatever is towards this way is the biggest. So 10 has the biggest atomic size. And then comes SI, and then C. Okay, C asks us to arrange the atomic size for magnesium, calcium, and strontium. So we have to identify these again: magnesium, calcium, and strontium. So remember, whatever is towards this area from the left to the bottom corner is the biggest atomic size. So strontium is the closest to this corner from all these three. So strontium has the biggest atomic size. Then it comes calcium, and then magnesium. Okay, D is F, Cl, and Br. So we have to identify F, Cl, and Br. So bromine is the closest to the bottom left, and so bromine has the biggest atomic size. And then comes chlorine and fluorine. Now we have to answer the second question to this problem. And it asks us, summarize what the trend is going across the periodic table and going down the periodic table. So after doing these problems, we can figure out that atoms decrease in size going from the left to right. Because remember when I was saying that atoms increase going this way from the right to left. So that's why atoms decrease in size going from left to right. Also, atoms increase in size going from the top to bottom, because atoms increase in size going down this way and to the left this way. That's why francium has the biggest atomic size out of all these elements. Now let's move on to problem number 6. Line them up. Part 2. How much attraction between the electrons and the positive nucleus dictate the ionization energy of the atom? Arrange each set of elements in order of increasing ionization energy based on periodic trends using the less than sign again. Summarize what the trend is going across the periodic table and going down the periodic table. A asks us to find O, N, and F, and O, N, and F are right here. And for ionization energy, it increases going up and right. Meaning that helium has the largest ionization energy. Okay, so we have to identify O, N, and F, and O, N, and F are here. Meaning that F has the largest ionization energy, or strongest ionization energy. So we know that that's the biggest, so that's greater than. And then it comes to O, and then lastly to N. Good job. Now let's do B. B asks us to identify aluminum, chlorine, and sodium. So we have to find where those three are at. So aluminum, chlorine, and sodium. Okay, so chlorine is the closest to helium that way. So chlorine has the strongest ionization energy. So we put chlorine here. Then it's aluminum. And lastly, sodium, because it's on the opposite side. The farthest out of these three to helium. C. We have to identify lithium, sodium, and potassium. So lithium, sodium, and potassium. So lithium is the closest to helium out of these three, meaning that it has the highest ionization energy. And then following sodium and potassium. Okay, D. D asks us to identify the ionization energy of potassium, calcium, and bromine. So potassium's right here, calcium's right here, and bromine's right here. So it's 19, 20, and 35. So bromine is the closest to helium, so it has the strongest ionization energy. So Br. Then comes next calcium. And lastly, potassium. So now we have to answer the second part of the question 6. Summarize what the trend is going across the periodic table and going down the periodic table. So after doing these problems, we can figure out that ionization energy increases going from left to right because it increases this way. Therefore, helium has the highest ionization energy. Also, ionization energy decreases going from top to bottom.